Good day. In this video, I will discuss some of the PT problem fourth pass lesson.
For PT number 1, calculate VO in the circuit in figure 1.20. First, we will convert the inductance and the capacitance. As we can see here, 0.5 Henry will be converted to its rectangular form. The formula for the inductance is W times the inductance 10 times 0.5 is now equal to J5. For the capacitance, 1 over 20 farad will be converted to its rectangular form. The formula is 1 over WC. 1 over 10 times 1 over 20 is now equal to J2. As we can see in the voltage source, we can convert it to its polar form or rectangular form. 10 cos 10t plus 75 degrees is now equal to 10 bar angle 75 degrees. Or in the rectangular form, 2.5882 plus J9.6593 volts. Next, we will simplify this circuit. 0.5 Henry parallel to the 10 ohms or the J5 parallel to the 10 ohms. For Z1, Z sub 1 is now equal to J5 times 10 over J5 plus 10. It is equal to 2 plus J4. For our Z sub 2, it is equal to J2. Using the voltage divider theorem, the formula for V sub 1 is Z sub 1 over Z sub 1 plus Z sub 2. It is equal to 2 plus J4 over 2 plus J4 plus J2. It is equal to 0.7 minus J 0.1 volts. For our V2, V2 is equal to Z sub 2 over Z sub 1 plus Z sub 2. J2 over 2 plus J4 plus J2 is now equal to 0.3 plus J 0.1 volts. For this problem, VO is equal to our Z sub 2. The answer is 0.3 plus J 0.1 volts, or in polar form 0.3162 bar angle 18.4349 degrees volts. Now for PT2, find current I in the circuit in figure 1.21. First, we will simplify the impedances in series like 8 ohms and J5 ohms, 5 ohms and negative J2 ohms. This part we will treat it as impedance A, and this part will be impedance B. Impedance A is now equal to 8 ohms plus J5 ohms, and impedance B 5 ohms minus J2 ohms. And we will redraw the circuit. Now this is the big letter A, the J4 ohms. The big letter C is the negative J3 ohms. And the big letter B is for impedance A. And this delta will be converted to Y. The formula for Z1 is A times B over the sum of all the impedances, the J4 plus 8 ohms plus J5 plus negative J3 ohms. For Z sub 1, the formula is A times B over the sum of the impedances. For Z sub 2, C times B over the sum of impedances. Z sub 3 equals A times C over the sum of impedances. For Z sub 1, A is equal to J4 times the impedance A, 8 ohm plus J5 over the sum of impedances is equal to 0.2 plus J 3.76. For Z sub 2, C times B, the value of C is negative J3 ohms times the value of B, which is our impedance. Impedance here, the impedance A. Negative J3 times 8 ohms plus J5 ohm over the sum of impedances is now equal to negative 0.24 minus J2.82. For Z sub 3, A times C, the value of A is J4 times the value of C is negative J3 ohms. J4 times negative J3 ohms over the sum of impedances is equal to 0.96 minus J0.72. And the circuit is now redrawn to another circuit. This is the Z3, the Z1, and the Z2. And we will copy the impedance B, which is 5 ohms minus J2. This is the value. And the 10 ohm is here. Then we will simplify the circuit again. For this impedance, we will find its series. A Z1 plus the impedance B is equal to 0.32 plus J3.76 plus 5 minus J2. Simplified, 5.32 plus J1.76 ohms for this simplified series impedance. Now for the series part B, this part is the Z2 and this is the 10 ohm. Z2 is equal to negative 0.24 minus J2.82 plus the 10 ohm resistor is simplified to 9.76 minus J2.82 ohms. And this is now the simplified circuit after the series in impedances. Now, this A and B is parallel. So, the formula for parallel impedances is A times B over A plus B. And it is in series with this component, which is our Z3. Our Z3 is equal to 0.96 minus J is 0.72. First, the parallel part, 5.32 plus J 1.76 times 9.76 minus J 2.82 all over 5.32 plus J 1.76 plus 9.76 minus J 2.82 plus the Z3 0.96 minus J 0.72 is now simplified to 4.7037 minus J 0.3126 ohms. This is now the equivalent impedance of the circuit. For us to get the current, we will use the Ohm's law, which is voltage over resistance. For this time, current is equal to voltage over our impedance equivalent. Now, 30 over 4.7037 minus J 0.3126 is now equal to 6.3499 plus J 0.4220 ampere, or in polar form 6.3639 bar angle 3.8022 degrees ampere. For practice problem 10.4, calculate current I/O in the circuit of figure 10.11. Our expected answer is 5.075 bar angle 5.943 degrees ampere. We will find current I/O using mesh analysis. First, we will assign the flow of current. First, the I/O, the I1, the I2. As we can see, we use the super loop combined because of the current 2A affecting the current I1 and the current I2. Next, we will assign signs for each of the component in the circuit. This I/O prime is also just the I/O. And for mesh I/O, we will use the KVL, which is negative 50 plus 10 I/O plus I/O minus I1 affecting each other times the negative J4 plus I/O minus I2 affecting each other times the 5 ohms. We will simplify it. Negative 50 plus 10 I/O minus J4 I/O plus 5 I/O plus J4 I1 minus 5 I2 equals 0. Then, we will combine like terms. 10 minus J4 plus 5 I/O plus J4 I1 minus 5 I2 is equal to 50. This is our equation 1. Now for our super loop, we will start here. I1 minus I/O times negative J4 plus J8 I1 minus J6 I2 plus I2 minus I/O times 5 ohms is equal to 0. We will simplify. Negative J4 I1 plus J4 I/O plus J8 I1 minus J6 I2 plus 5 I2 minus 5 I/O is equal to 0. We will combine like terms. J4 minus 5 times I/O plus J4 I1 plus 5 minus J6 I2 equals 0. This is our equation 2. For our node A here, using KCL, we will get I1 plus I2 because current flowing here plus the 2 ampere flowing here is equal to the output flowing here, which is the I2. For us to get the missing variables, we will transform the formula. I1 minus I2 equals negative 2. The positive 2 is converted to negative 2. This is our equation 3. As we can see, we have the 3 equation, and to get each variable using our calculator mode, solve system equation 3 unknowns, we will input each of every variable of our equation 1 for the first row, equation 2 second row, and equation 3. And for the x variable, it is our I/O, y variable is I1, and the z variable is I2. I0 is equal to 5.0473 plus J 0.5254, or we can convert it to its polar form, 5.075 bar angle 5.943 degrees ampere. We only get the x variable because it is the value of our I0. And the problem here is to calculate only the current I0 in the circuit, and our expected answer is 5.075 bar angle 5.943 degrees ampere, which is the same. For practice problem 10.2, calculate V1 and V2 in the circuit shown in figure 10.6. First, we will convert the polar form of the voltage source, and here the voltage source here, to its rectangular form. 15 bar angle 0 degrees is equal to 15 volts. 20 bar angle 60 degrees is equal to 10 plus J 17.3205 volts. Now we will solve for the node for V1 and V2. As we can see, this is super node. We will solve super node using KCL. 15 minus the V1 over 4. 15 minus V1 over 4 equals to the V1 minus 0, the ground, over J4, minus V2 minus 0 over negative J1, already here, plus the V2 minus 0 over 2 ohms. We will simplify this using its GCF, which is the J4. J4 over 4 equals to J. J times 15, J15. J times negative V1 is negative JV1 equals to J4 over J4 is 1 times V1, positive V1, minus J4 over J1 is 4 times V2, 4V2, plus J4 over 2 is J2 times V2, J2V2. We will simplify this as V1 plus JV1 minus 4V2 plus J2V2 equals J15, and combine like terms. 1 plus JV1 plus negative 4 plus J2V2 equals J15. This is our equation 1. For our equation 2, as given here, when we subtract V1 and V2, we will get the voltage 20 bar angle 60, which is 10 plus J17.3205. V1 minus V2 is equal to 10 plus J17.3205 for our equation 2. Now, using the matrix method in our calculator, we will get the coefficient of each variable, 1 plus J, negative 4 plus J2 for our V1, and J15. For our V2, 1, negative 1, and 10 plus J17.3205. We will get for our x variable is for V1, 6.7265 plus J18.1538 volts, or in polar form 19.3599 bar angle 69.6689 degrees volts. For our y variable for V2 is equal to negative 3.2735 plus J 0.8333 volts. In polar form, 3.3779 bar angle 165.7182 degrees volts.